Good morning, everyone. It is 10 o'clock in the morning on Saturday, the 25th of July. So it is time for the Physics with Keith tutorial. And this week we're looking at the first section, the first week of the summer school that I thought I'd try to run. To which we've had 10 people subscribe, which is quite exciting. So to the 10 people out there, hello and good morning. Currently it shows 2 people are watching, although I think one of those is me. So one person is out there watching in the internet. So hopefully those 10 people that are subscribed will play along. Maybe they'll be watching this a little bit later. But this is a live tutorial. Now, because it's a live tutorial, that means that you can communicate with me in real time. I can ask you questions and you can ask me questions and so on. In order to do that, the easiest way is to use the YouTube live chat feature. And to use the YouTube live chat feature, let's just switch this across to show you. On the chat window, you can see there's the, on YouTube, where the video is playing, and then just to the right of it, or depending on how you're set up, it might be just below it, there's a little chat window here, and you can type in something there. So just to show you what that stream looks like, I mean, it's currently streaming what's on the left here, but I can type in, for example, the word hello, and then we all get that message. Now it takes about 7 seconds between me saying something and you hearing it. So factoring that 7-second delay, it means that if you type a question or type an answer or something, don't think that I'm ignoring you if I don't respond straight away. Because I have got this open on my screen, so I will be able to see in real time. Now I had a look to see how many people had been attempting the questions that had been set, the Isaac Physics questions, and it looked to me like not very many of you, to be honest with you. When I was looking all the way through the week, it was 0 people had attempted the questions, and then a little bit later on, one person, hello, good morning, someone's just said hello on the message. A little bit later on, as in about half an hour ago, I checked again, and one person had attempted 1 question. So yeah, if you want to get the most out of this, it really is worth trying these questions rather than just watching the videos. Physics is the sort of subject that you get better at by doing it, not just by watching other people do it. So my strong advice to you is to log on to Isaac Physics. You've got an account with Isaac Physics already, and make sure you're connected to the group by using that link in the instructions that I sent out on Facebook. I just had a little message here saying school only finished on Wednesday and not had time. No, I completely understand. I'm just giving everyone a bit of a heads up. If you make sure you are checking those questions, giving it your best shot, then I can check just before the session, see which questions are causing the most problems, and then fine-tune these tutorials to those questions. At the moment, because very few people, I've had 1 person attempted 1 question, I don't have a lot of data to go on, so I'm going to have to pick some questions at random to go through, unless anybody says that there are any they particularly want to look at. So the board of questions that I had set was here. You can just see that on the left of where my face is. All about mechanics, and you see that I've selected from chapter 8, chapter 9, chapter 10, 11, 12, 13, and so on. So across the whole of the mechanics section, I've picked a few questions. And what I've tried to avoid is questions that test the same skill. So often with Isaac Physics, you'll do a whole board of questions where they all test the same sort of skill, and you get better and better and better at it, and then you've mastered it by the end. I thought through this summer school we'd try something different, and rather than doing that, we would have lots of different sorts of questions, and we'd be able to identify very quickly if there's any that you need help with, rather than just drilling you to practice the ones as we go along. So looking at this board of questions, you don't really know what the topics are about unless you know the topic numbers. If we start from the first one, 8.6, this is quite a straightforward question. So if you looked at 8.6, you'd see it says a long distance runner has an average speed of 5.5 meters per second, and how far would the runner go in 30 minutes? So we have a speed of 5.5 meters per second, and we have a time of 30 minutes, and we want to know a distance. And if you remember from the video, that I put up there about this time last week. In our equation, speed equals distance over time, s is not the speed, v is the speed. And I think I said in the video, please don't ask me why, because I don't know. It's just the way it always has been. So we're after the distance. The equation would be distance equals speed multiplied by time. However, if you look at these units, meters per second and minutes, so they are not compatible units. If I multiply the unit meters per second by the unit minutes, I end up with a distance in meter minutes per second, which is a unit of distance, but it's a peculiar one that no one would ever choose to use. So to be consistent, to make it so that when we write meters per second and multiply it by a unit in seconds, the units will cancel, which is what happens when you've got a number on the denominator down here and a number on the numerator up here. They can cancel out, so we end up with meters left behind. So that's what we want to do. So first of all, we need to convert this time into seconds. 30 minutes multiplied by 60 seconds per minute equals, and so we can go 3 times 6 is 18, so that's 1, 8 and 2 zeros. I think that's right, just doing that off the top of my head. And do shout at me if I get this wrong, because my mental arithmetic is not great. And now I can do my sum here. Displacement or distance, this is a distance, equals 5.5 times by 1800 seconds, and for that I'll need my calculator, which very grateful to Swiss Micros. They sent me a replacement screen for my calculator after the last one broke within a week of breaking it, which I was very happy about. So this is 9.9 times 10 to the 3 in standard form. Now if you're not comfortable with standard form, we've not seen this before, don't worry, I'll write it in the usual way and we can talk about standard form another time. That's 9,900 meters, which is the same thing as 9.9 kilometers. So what you do on the Isaac Physics website is you've worked it out, you choose your unit, and we're going to choose either meters or kilometers. I'll go with meters. We're going to write 9, oopsie, I scrolled up, numlock isn't turned on. We type in 9900 and it says correct. And there we go, and it gives me the answer whether I'm right or wrong. So that's how the Isaac Physics is going to work with this. As you go through the questions one by one, you'll find out which questions you can do and which ones you can't do. And I will know which ones you've tried and managed and which ones you've tried and not managed, and that will help me with my planning of each week. If you find one that you can't get right, you can keep trying it again and again. There's no limit to how many times you can try it. The only limit really is how long you're willing to spend on it. So a car moving at a speed of that, round about the diameter of that. So this question has is a little bit different because we're talking about going in a circle. So I'm just going to take a screenshot of this question so that I can put it on my same screen while I'm working on it, so we can see all the numbers. Scroll up a bit more. Oops, that was a bit too far. Okay, that'll do. Okay, so we've got a car moving a speed of that, round about the diameter of that, that's the thing, and we want to know the distance the car has travelled. So it's the same equation as last time, distance equals speed multiplied by time. And we've got the speed and we've got the time. It says that the car's moving at a speed of that, and after that far on the roundabout, how far has it travelled? We don't really care about the diameter of the roundabout. It's sort of irrelevant for this, to be honest with you, because we've got this distance, we've got the speed, and we've got the time, so we can just multiply those two together. 10.0 multiplied by, and I've used 10.0 because this number has 3 significant figures, and if you don't know what significant figures are, that's okay. Quick rundown of significant figures. Significant figure is anything 1, 2, 3, 4, 5, 6, 7, 8 or 9. with 1 being the least significant figure. And so if I write a number like 0020, the first 2 zeros are not significant, and so the number of significant figures in that number is 2 significant figures. If I write 02001, in that number, the first 0 is not significant, so this number has 4 significant figures. If I write down 0.00102, then the first bunch of zeros are not significant, and that is a 3 significant figure number. So that's how significant figures work. So what we've got here, and by the way, if I went too quick with that, do tell me, do shout at me and say, whoa, slow down. So what we've got here is a 3 significant figure number and a 4 significant figure number. And when we do any sorts of questions in physics, our final answer is given to the lowest number of significant figures in the data that we used in the calculation. So we're going to give our answer to 3 significant figures, because 10.0 is 3 significant figures, but 23.56 is 4. So 10.0, 23.56, multiply them together, you get 235.6. That's to 4 significant figures, 235.6. We want to give our answer to 3 significant figures, so that will be approximately 236 meters. We're going to check the units. We always check the units before we move on. Meters per second multiplied by seconds leaves us with meters. So let's check it, and hopefully we got this right. 236, and meters. Correct, that's reassuring. But that's only the first part of the question. So once you've done that, it then moves on to the second part of the question, then the third part, then the fourth part. So the second part of the question, how many turns of the roundabout has the car made? So the car's going around a roundabout. We know the diameter of the roundabout, which is given here as 50.0 meters, and we know that we've travelled a distance of about 236 meters. In fact, I'm going to use the unrounded number in my next few calculations. That's normal. You round the number for your answer, but if you need to use that answer in any subsequent calculations, use the unrounded number. So, if I want to know how many times I've gone round in a circle, I have to know the circumference of the circle. And the circumference of a circle is calculated as 2 pi r, or pi d. We've given the diameter of d, so pi multiplied by d is going to be, well, pi multiplied by 50.0. Does that fit on the screen there? It might just be hidden by my logo. When I scroll, it'll be okay. Or I can just turn my logo off for a second, just while I'm writing. So pi, so you take your calculator out, you type it in, you don't have to remember pi, you can just type it in, multiplied by 50, and that gives us 157.1. So let's get my pen out, 157.1 meters. That's the circumference of the circle, and we travel a distance of 235.6 meters. So basically the question is, how many times do we go around our circle? So if we do the distance we travel divided by the circumference of a circle, that tells us how many times we've gone around our circle. The number of times we've gone around the circle is going to be 235.6 divided by 157.1, close to it. So 235.6, and do that. That's 1.5 times. Now, if you're not sure why that is, shout at me. Go on the comments thing and say, Keith, stop, explain this to me. I don't understand. You've made a jump there. I don't understand it. That's the whole point of this being interactive, is that you can ask me for help. If we were in a classroom, I'd be able to see the confused look on your face and know if I needed to explain it a bit more or not. If you understand this, then you carry on. Just let me know you get it, and I can keep going. So that's the number of times we've gone in our circle. Total distance travelled divided by distance per circle equals number of circles. 1.5 circles. So let's, oopsie, that's all my various files that I'm working on. Let's pop that into Isaac Physics. How many times do we go around? Oopsie, 1.5. And then it'll say magnitude of the displacement. What is the magnitude of the car's displacement from where it entered the roundabout? Now for this one, you have to visualize what's going on. We've got our roundabout here. In fact, let's do a quick sketch. Here's my roundabout. Maybe it's got some roads coming off it like this. I think that's the quintessential roundabout. We enter our roundabout over here somewhere. We go around it like this 1.5 times, and then we leave it. And so the question is the displacement between this point here, let's label it A, and this point here, let's label it B. Well, that's the diameter of the circle, isn't it? You can see that from the quick sketch, that from one side to the other side is the diameter. And we were given the diameter in the question. In the question, it told us that the diameter of the circle was 50.0 meters. So let's type that in. 50.0 meters. Now, it might shout at me about significant figures here. Let's see. No, it's okay. The reason why it might shout at me is because when I did this, I wrote down 1.5. Really, I should have probably written 1.500, but it was nice and relaxed about it. He didn't mind. In fact, because I used the number 10.0, this should have been given as 1.50, and therefore I should be giving my diameter to 3 significant figures, which I think I have, haven't I? Yeah, so that's why it's right. If anything, it should have shouted at me about this one and said, no, that should be 1.50. Anyway, there we go. Distances on and across circles. So this question says, at the very start, t equals 0, is it possible for the distance the car has travelled to equal its displacement at any point on the roundabout? That's a difficult question. So what we're saying is, as you go around, is it possible that you travel the same distance as your displacement? And you really need to try to visualize what's going on here. The displacement is a straight line from the starting point to where you are, and the distance you've traveled is the curved line that goes around. So if we scroll down to this, let's draw a little circle to make it easier for us to explain what we're talking about. There's a nice little circle. And let's have our starting point of, let's have it on the very top here. So there's the starting point. If we just pick any position round here, B, and then draw our line connecting A to B, you can see that the line A to B, the displacement, is shorter than the distance, that curve. You can see that. So the question is, as we move around, is it possible to have it so the distance is equal to the displacement? Well, we can ignore anything where we're travelling around in this direction. We can ignore anything where we've travelled beyond point C. Because beyond point C, the distance will continue to increase, but the displacement will decrease. So we can ignore that. So if we just look at this section between A and C, this curved section around here, A to C much shorter than the distance around A to C. Some arbitrary point on the side, that distance is still bigger. And in fact, you can go all the way around here and it's just not possible. Your displacement will always be less than your distance when travelling in a circle. You can see it you can visualise it. So here we've got two options for no. Either no because the distance depends on the radius of the roundabout, whereas the displacement does not, or no, as the distance travelled is an arc and of the circumference and the displacement is a chord. That sounds more like the correct one. And if you're not sure what a chord is, or an arc, if you haven't done that in maths yet, please don't worry too much about it. It's good to know, but it's not really required for a GCSE in physics. So, a little reminder that this is a live tutorial. Do ask questions. If you need me to go through any of these parts again, or if you understand them, just, make some noises. Say, yes, I understand it. That's great. Thank you, Keith. I'm here to help you, so make sure you keep that communication going. We're going to look at some more of these. We will not have time to do all of them. That's the downside. So let's try another one at random. Let's try 11.10. That looks like it might be a slightly trickier one. So 11.10. An overtaking lorry on a straight section of road It says a driver increases speed from 50 miles an hour to 70 miles per hour in 5 seconds, and we're given a conversion here. Calculate the acceleration. And we're asked to calculate the acceleration in miles per hour per second and the acceleration in meters per second. So let's take a little screenshot of this. We've talked about speed equals distance over time. Now we're talking about acceleration. So let's scroll all the way down here. Actually, let's just paste it there. Scroll down there. Okay, so let's start off with miles per hour per second. The difference in speed divided by the time between those two speeds. That's what the acceleration is. So a difference between our two speeds is 70 miles an hour minus 50 miles an hour divided by, is taken 5.0 seconds. And that will give us an answer in miles per hour per second. So that's 20 divided by 5. Don't need a calculator for that. That's 4.0 miles per hour, a rather non-standard unit, per second. And that's a unit of acceleration. Miles per hour per second. So if we go on to here, miles per hour per second, 4 points. How many significant figures shall we have? I can't type today. 2 significant figures. Always check your significant figures, and that's fine. Then it says meters per second per second. So we're going to have to do some conversions now. Now, fortunately, we are told what the conversion is. So let me teach you how to do conversions. Let's get rid of all this. We don't need this for now. Let's first of all convert 50 miles per hour. 50 miles per hour. Now, this is going to sound odd, but let's go with it. If I multiply that by 1, it doesn't change. I hope you agree with that. Multiply that by 1, it doesn't change. The number 1 doesn't have a unit. The number 1 doesn't have any dimensions. It doesn't represent a distance or a time or a mass or anything like that. It's just the number 1. Multiplying anything by the number 1 doesn't change what you're multiplying. Now, it's also true that the number 1 is what you get when you divide something by itself. 5 divided by 5 is 1. 10 divided by 10 is 1, and so on. But sometimes we're going to have things that are the same, but they are written differently. For example, let's take a ruler out here to show you what I mean. Oh, where's my ruler? Here it is. On my little ruler here, I've got, this is a 13 centimetre ruler. Don't be put off by that, it's because it's a slide rule. So let's switch it across. 13 centimetre ruler, so that's 13 centimetres, but that distance of 13 centimetres is also about 5 inches. So if I write 5 inches, I'm saying that's what I'm representing, this distance here. And if I write down 13 centimetres, it means the same thing. It's this distance here. Switch it back across. So what we're saying is that if I divided the 13 centimetres by the 5 inches, it would pretty much equal 1. In fact, if I wrote down 2.54, I think it is, 2.54 centimetres divided by 1 inch, that would be the number 1. And so we're given a conversion here. And I can say that 1 mile per hour on the bottom and 0.45 meters per second on the top. Because this speed, 0.45 meters per second, is identical to this 1 mile per hour, this fraction is just 1. And because it's a speed divided by a speed, its speedness, its speed essence cancels out as well. But what doesn't cancel are the units. And so you can use this to convert units. So let's multiply my 50 miles per hour by this fraction. 1 mile per hour, and then on the top 0.45 meters per second. Now if I do this, the miles per hour will cancel, and I'm left with meters per second. There it is. So that's how I can convert my speeds. So let's convert our speeds by multiplying by 0.45. And my 50 miles per hour becomes 22.5 meters per second. And my 70 miles per hour becomes, so 70 multiplied by 0.45, 31.5 meters per second. And so my difference in speed is going to be 31.5 minus 22.5, and that is 9 meters per second. And so my acceleration is going to be the 9 meters per second divided by 5.0 seconds, and I get 1.8 meters per second, which we write as meters per second squared. So acceleration question, difference in speed divided by time, or this difference in velocity, it should be divided by time, but we have to do a unit conversion, and that makes it a little bit more complicated. So 1.8, correct, that's good. It's always reassuring when it comes up purple and says them right. So let's pick a different one, shall we? Let's pick a different one. Should we go for 16.7? As I say, I'm not going to have time to do all of them, so let's just pick some at random, really. So this is another part of mechanics, is balancing. And we're balancing weight A, weight B on the end of a beam. And you can see A is twice the distance away from what's labelled the fulcrum, sometimes called a pivot in the middle. F is twice the distance to A than it is to B. So it says if A weighs 5 newtons, what's the weight of B? I don't really need to do any calculations for this one. Because A is twice the distance away, it has to have half the force to get things to balance. Or in other words, B, which is half the distance, has to have twice the force. So that's going to be 10 newtons. And then it goes on. And the question carries on with similar sorts of parts to it. Let's just shrink that. Some different things here. And this time you can use the ratio. So you can say A is 10 newtons. We know B is going to weigh more than 10 newtons, but how much more? We could do 36 divided by 25 to say, look, A is 1.44 times further away, so B has to have 1.44 times the force. And 10 times 1.44 is 14.4. But we're going to go for two significant figures, so let's just call it 14 newtons. That's the weight. Newtons is the unit of weight because weight is a force. And it's the same thing again and again here. So I think you get the idea now. A here is 10 newtons, but it's also 4 times further away than B. So that means B has to have 4 times the force, 40 newtons. Correct. And weight C. This is where it gets interesting. So let's have a look at the next part. So part D, it says weight C. We've got A and B, and now we want to find out C. This is where students sometimes find this a lot more challenging. So let me show you how to do it properly. Actually writing something down. Let's take a little screenshot. Paste that there so I can draw on it, and I might have to shrink this a bit to give myself a little bit more room. Hopefully that text is still visible. Hopefully. So let's start with the principle of moments, and that's that the total moment clockwise will equal the total moment anti-clockwise if this thing is balanced. In other words, if its rotation isn't changing. In this question, the rotation isn't changing. So let's write down a little table of clockwise and anti-clockwise. So we've got clockwise moments, and we're going to put next to it anti-clockwise. It's gone off the edge of the screen. My big head's covering it up. Anti-clockwise moments. And so clockwise moments. This is trying to produce clockwise moment. This is trying to produce clockwise moment. They're trying to rotate this thing clockwise around the pivot. So let's use a color coding thing here to make it a little bit clearer. Let's use blue for clockwise. We want the weight of C. So we know whatever the weight of C is multiplied by 30 centimetres is one of the things that's producing that clockwise moment. The weight of A we are given, which is 10 newtons, multiplied by, well, what's the distance for A? I would ask you and get you to type the answer, but I'm just going to keep going because I'm not convinced people have tried it, and if they've not tried it, I don't just want them guessing by themselves. It's not just 30 centimetres, it's 60 centimetres. That's the distance from A to the pivot, 60 centimetres. And so that's on this column of clockwise moments. In the column of anti-clockwise moments, we've got this one. This one's trying to rotate everything around anti-clockwise. So in the column of anti-clockwise moments, we've got 45 multiplied by B. B is 20 newtons, and there we have it. So now if we write this as an equation, we can say that C times 30 plus 10 times 60 equals 20 times 45. Now we want to get the C as the subject, because that's what we're trying to find. So to get C as the subject, we use our order of operations in reverse, our operator precedence in reverse. And so what we're going to do is get rid of this part first, and then we'll get rid of this part second. So C multiplied by 30 is going to equal 20 times 45 minus 10 times 60. So we've got rid of that by subtracting it from both sides. And C is going to equal, let's divide through by 30. And again, this is a place where students make mistakes very often. They'll just divide one of these terms on the right by 30. In fact, they are both divided by 30. The whole right-hand side is divided by 30. Take our calculator out and we put that in. So 20 enter 45 times, 10 enter 60 times, minus 30 divide, and we get 10 newtons. And hopefully that's right. So we get the thing open, type in our 10 newtons. Okay, good. And job done. And then it goes on, and it's the same sort of question again. I'm not going to bother doing this one. You can do this one yourself. But use the same approach of stacking up your clockwise and anti-clockwise, then writing out like that and putting your numbers in. Okay, so let's go back to the board. Now the question is, are there any of these others that you want me to look at? Any that you've looked at in particular? So what I'll do is I'll open up each one, tell you what the topic is, make a note of any that you want to go through, and then let me know on the chat if there are any you want me to go through. So 10.3 was about graphs, displacement time graphs. 12.3 was about speed time graphs. 13.1 was about vectors and resultant vectors. 14.7 was about, I don't know what this is about. Oh, okay, this looks like it's about terminal speeds. Turbulence. Actually, this is quite a nice question, bit of a tricky question, but it's about terminal speeds and the effect of air resistance. Basically, what happens with drag. 19.8 is about forces and acceleration and how they're related to each other. So Newton's second law. And 20.9 is, again, it's about Newton's second law, but this time it's changing mass instead of changing velocity. So are there any of those you want me to go through? Speak now or forever hold your peace, and we'll call it a day. No questions have come through to Facebook Messenger yet. Not so strong on displacement, so please could we go through that? Yeah, do you mean the displacement time graph? Happy to look at that. So the displacement time graph, here we have it. We've got displacement on the y-axis. Remember, displacement is just a distance that you've travelled, but in a particular direction. Sort of a straight line from starting point to finishing point as the crow flies. That's what the displacement is. The thing we call displacement carries with it information about how far, but also which direction a point is displaced from an origin. So this graph of displacement versus time, there's a lot of steps on it, and it says between which times is the velocity most negative. Now the velocity is represented by the gradient of a displacement time graph. And so if you look at this gradient, which is what we call the slope, is positive here because it's sloping upwards, and then it's positive in this leg of the journey here, and then the gradient is 0, then the gradient is negative in the fourth leg of the journey here. And the question says between which times is the velocity most negative? Well, the velocity is the gradient, so if the velocity is to be most negative, the gradient has to be most negative. So we're after the steepest negative gradient, and I reckon it's there. So now we read off our axes, and we say this is 50 seconds to, what's that, 65 seconds. 50 to 65, I think it's that one. It is that one. Okay, so that's how we looked at that question. It then says calculate the most negative velocity during the motion. So in other words, now you've found out what it is. What is that most negative velocity? And so it's the final displacement minus the initial displacement divided by the time it's taken. So let's scroll down. Give myself a bit of room. So final displacement minus initial displacement. The final displacement at the end of the leg of the journey is here. And so that's going to be negative 15 meters. Now we have to subtract this initial displacement, which is here on the left, which is, so we subtract 20. And just be careful of your signs here. Minus 15 minus 20. Then we divide by the time. So what we're doing is we are taking the gradient of this line. There's our time. If you look, we can see that the point here is there and the point here is there. So the time is between this time and this time. And each of these little squares is worth 5 seconds. So that's 15 seconds. So what we're doing is the difference in the y direction divided by the difference in the x direction. That is a gradient. So let's plug that into our calculator. Minus 15 minus 20 minus 35 divided by 15, and we get, is that right? So minus 35 divided by 15, yeah, it looks right, minus 2.3, and we're not going to call it recurring. We never do that in physics. We're going to write down minus 2.33. We might even put a fourth significant figure in. It doesn't matter. And don't forget the unit. But before we put it into Isaac physics, we're going to have to round it to what we think is suitable. I reckon maybe 2 significant figures, 2.3. So we're going to here. I'm going to put in 2.3 meters per second. Where's my meters per second? Why have I got millimeters per second? Have I read the graph wrong? I have read the graph wrong. Look, this is in millimeters. What a silly thing to do. Well, it doesn't matter. It's millimeters per second anyway. It says, it should be negative. Of course it should. I said it was negative, and then I didn't actually write it down. Negative 2.3 meters per second. So you can see what I mean. The Isaac physics tells you if you put the answer in wrong, which is quite a handy thing. Let's just have a look and see. Yeah, I put it negative there and then didn't type it in. Foolish of me. Okay, so then we can look at the times most positive. So when is it most positive velocity? So in other words, when's it steepest? And just looking at the graph, I would say it's here and here is when it's steepest. That's what I reckon. So it's 2 times when it's steepest, but it looks equally as steep there as it does there. So between which of these times is the velocity most positive? That's between 70 and 80, or between 90 and 100. 70 and 80, 90 and 100. So I'm going to put this one. Correct. Okay. There are 2 possible answers, but as it was a multiple choice, there's between 90 and 100 second option wasn't there. So then it says most positive velocity. So calculate the most positive velocity. We're going to do the same thing. So we can take the final velocity, which is 10, subtract the initial velocity, which is minus 10. So that's an increase of 20 millimeters distance. Did I say velocity? I'm so sorry. The displacement is 10 millimeters here, is negative 10 millimeters here. So 10 minus negative 10 is 20 millimeters divided by 10. So 20 divided by 10 is 2. So that should be positive 2. Always a risk not using a calculator, so let's see if I get that right. 2, and it's positive this time. I'm going to put 2.0 because I'm going to try and keep consistent with the last question. And I think 2.0 is sensible given that scale. Correct. Times of the highest speed, between which times is the speed highest? Okay, now we have to be careful, because speed is the magnitude of the velocity. So in other words, when is it the steepest gradient, but we don't care if the gradient is positive or negative? Well, we've calculated the most negative already, and we've calculated the most positive. So what we're saying is, which of these 2 numbers has the biggest magnitude? Negative 2.3 or 2.0? Well, the answer is negative 2.3. That's the most negative velocity. It's also the highest speed. We just happen to be going backwards. And that was between the times of 50 and 65 seconds. So we can scroll down here and put 50 and 65 seconds again, and it's fine, it's correct. And it says, what is the highest speed? Well, it's 2.3 millimeters per second. Because we'd already calculated it. We don't have to do any more calculations for that. And then finally, what's the lowest speed during the motion to the nearest integer? Now this could be a little bit controversial, couldn't it? The lowest speed, because if you look at the graph, there's a lot of scrolling here, but if you look at the graph, the speed in this section here is 0, but it's not moving. So how do we interpret this question? Calculate the lowest speed during the motion. Should I put 0 and see if that's right? Oh, it is right. Okay. Or should I put down the lowest speed whilst moving? Now, because this is a graph of the motion of something, the fact it's not moving here doesn't mean that we can discard it from this graph of the motion. If they wanted you to discard that and have the lowest speed but it's still moving, it would say the lowest speed while moving to the nearest integer. So, okay, that was interpreted correctly. So hopefully that's a little bit helpful. That was going through this displacement time graph and how to understand reading data off a displacement time graph. Can be a little bit tricky, especially because displacement time graphs, displacement is a vector, and so they can throw scalars at you. And if you're not quite sure what vectors and scalars are, don't worry, you can look it up. It's quite straightforward, or you can ask me about it. I can even go through it next week. That's fine. What I'll do now is record the video for next week, for the next session. I'll either record that today or tomorrow and get that uploaded, and I'll set the assignment as well. I'm hoping to get all that on there before the end of today so that you can work on that perhaps over the weekend, or you can work on that over the next week, ready for next Saturday. Now, as I say, there were 10 people that have signed up on Isaac Physics for this, which is very, very exciting. If you are wanting to join in with it, I really encourage you to try these questions yourself so that I've got an idea of what it's worth going through. Otherwise, I'm just sort of guessing and going through things that take my fancy. And this is more useful if I do things that would help you. No, you're very welcome. I'm very happy to explain that. No, I've realised as well that when I'm saying things, if someone watches this video back later and I'm responding to messages, they don't necessarily realise I'm responding to messages. A message just come through saying, thank you, you're very welcome, that's what I'm here for. So I'll sign off now. I'll put a little note on Facebook when I've uploaded the video, but if you subscribe to my YouTube channel, you will, there we are, a little subscribe icon coming up there. If you subscribe to my YouTube channel, then you'll get those notifications as well. Oh, one of my colleagues has just sent a message saying thank you as well. You're very welcome. I hope it was useful. I'm going to go now. I'm going to do some recording. Have a lovely weekend, and I will see you all next week. Stay safe. Thank you.